Hi everyone, welcome to our YouTube channel. In this lecture, we'll be building a linear regression model from the scratch. All right, so to do that, first we need to import our necessary libraries. Or let's just start documenting it as well. So build linear regression model. Okay, so very first step, we import the necessary libraries. So importing necessary libraries. Okay, so I need to import numpy pandas and a visualization library. Namely, we'll be importing over here matplotlib. All right. So import numpy as np, import pandas as pd, and import matplotlib.pyplot as plt. Okay. Next, we want to import our data, or let's also import the warnings library so that we do not see the deprecated warnings that it usually throws, right? Those are useless anyway. So import warnings, and let's just say warnings dot filter warning, sorry. Ignore. Okay. So we just imported our necessary libraries. Next, we want to import the data, right? So read the data, let's say. So let's create a data frame, df equals to pd dot read underscore csv. Now I have a CSV file with me, which I'll be sharing in the description. So housing.csv. Okay. And let's just see how df looks like. This is the head function. Okay, sorry, warnings. So what does head do? Head gives us the first 5 rows of the entire data frame, right? So 0 to 4. And this is exactly the data. So we have price, area, bedrooms, bathrooms, stories, main road, guest room, basement, hot water, heating, air conditioning, parking, brief, uh, preference area, and furnishing status. So based on all these features, right, we are predicting the price of the house. All right. So ideally, it is not a simple linear regression problem because it has so many features, right? This would be an ideal case of a multilinear regression, but we have not learned about it. So what we can do is we can extract only one feature and the target remains as price, right? So even before doing that, let's quickly uh, do a data pre-processing, right? Let's just clean the data. So let's see if the data has any issues. All right. So just to check it, let's say df dot is null. I just want to check if it has any missing values or not. Dot sum. Let's just say dot sum. So it says it gives me directly. So there is no null values. Great. So we are clear of any null values present. So no treating of missing values needed. Let's quickly check if there is any duplicate values. So df dot duplicated, right? Let's just take it inside. Okay, again, so there is no duplicate values present as well. Great. So no duplicate, no missing values. We are good to go. Uh, let's check for any data discrepancy might be present if there at all. So I'll just do the info function. Okay. So obviously, and what is the size of the data? Let's just also find the data size. So df dot shape, it gives me 545, 13. So 13 columns and 545 rows. For all the features and the target, what we can see is 545 non-null. Great. Most of them are integers, which is fine for the machine learning model to create. However, there exists some sort of an object data types as well. Now, an important problem over here is machine learning cannot take object data types. So we have to do some uh, what we call as encoding of categorical columns. So this that we see over here are categorical columns, that is with object, and we need to convert them to numerical columns. So ideally we use ordinal encoding or uh, one-hot encoding, right? Ordinal encoding whenever the data type is ordinal. Otherwise, one-hot encoding. But here, just to save time, we'll simply go with label encoding. But ideally, you should never use label encoding in your features. Label encoding is only reserved for the uh, dependent variable, that is the target variable. But here, since our goal is not to do a proper data manipulation or data wrangling, we only want to understand how linear regression works. We can skip this, beautification. We'll simply go with label encoding because it's easy, right? Okay. So how do we do label encoding? From sklearn.preprocessing, import label encoder. Okay. Let me just call a object to the class label encoder so that we can use it all over. Okay. So what are the columns that we need to change? We need to change main road, guest room, basement, hot water heating, air conditioning, furnishing status. These are and reference area, right? And preference area. All right. So let's do them one by one. So df of main road. Okay. So in order to take the columns, let me simply say df dot columns. Okay. So first thing that I want to take is main road. So df of main road equals to le dot fit underscore transform df of main road. So what it does is it takes df of main road and it creates an object to the class 11 encoder. That is, whenever it finds object type data, it converts using label encoding to numerical values. So fit, that is, it gets trained using the column main road, and transformed, it then transforms the column main road. All right. So we need to do the same thing over all the object type columns. So how many object type columns are there? 1, 2, 3, 4, 5, 6, 7. So let me just copy it 7 times. 1, 2, 3, 4, 5, 6, 7. Okay. So what are the columns? Main road, then guest room. Okay. Then we have basement. Okay. Then we have hot water heating. Okay. Then we have air conditioning. Great. Then we have reference area. Sorry, take it from here. And finally, we have furnishing status. Right. Okay, just a quick disclaimer. I called this df.columns just so that it becomes easy for me to copy from the column names. If you want to write it manually, you can do that. If you want to take it from here, you can do that as well, right? Great. So now we are done with our label encoding. Let's see how the DF actually looks. So let's see how DF looks before versus now. So let's just take df dot head. Before it looked something like this. Yes, no, categorical columns, all right. So now if I take df dot head, all has been converted to numerical values. All right. So what did we do over here? We did a label encoding, right? So we simply did some sort of a label encoding. Great. Now, as we said, we are done with all the data checkups. Everything is fine. Data quality looks good. But now we want to create a linear regression model, simple linear regression model. And we know our y would be price, the price column. What should be x? Any of the values we can take. We can take it at random. But what I was thinking is, let's take the one that has the highest correlation. What is correlation? Correlation means with change in y, change in x should be, x should also change. How much does x change is the measure of correlation. Correlation gives us a measure that with change in y, how much does x change? Okay. So what I'll do is I'll just find df of correlation. Okay. It would be somewhat difficult for us to find like this. Let's just do a heat map, right? So let me just import Seaborn. PLP. Okay, seems perfect. Now what I want to do is sns.heatmap. Let's just take df dot correlation. Okay. Let's also annote it. So what I'll do is annote equals to true, right? And I don't want this matplotlib line over here. So if you do not want this, either write pld.show or just put this semicolon. Okay, so now I get the annotated version as well. Area seems very highly correlated, 0.54. Other things I cannot find. I mean, this is the lightest color, so I believe area is the one. Another thing we can do to find the best correlated point is I'll simply do df dot core, right? And I'll find how the different features are correlated to the target variable, that is price. So it'll give me in a descending order. So price and price is obviously one. That is something that I should not be considering. Same thing, followed by area. So 0.53. Fine. We can take area as the feature, right? As the X value. So from the entire data set, what is happening now? From the entire data set, right? We had several features. One of them was area and the target was price. So what we are doing now is we are taking price and storing it as Y, and we are taking area and storing it as X. All right, that is what we are going to do now. Also, once we have segregated or splitted the data into two parts, X and Y, what we also do is we divide the data into training and testing phase. Now, what is this training and testing phase? So basically, we can train our model. We all know, right? The more the data, the better the trained model is. But the model also needs to be checked if it is, working perfectly or not. Is it getting, overlearned? So to understand the performance of the model, what we do is we, take out a certain portion of the data, which we call as the testing data, right? It is around 20%, 30%, something like that. 20 to 30 is the usual limit we take. So 20 to 30% is the data that we take out. And we call it as a testing data. All right. The rest of the data, that is 70 to 80% of the data, is what we use to train the model. Once the model is trained, we use the remaining 20 to 30% to test the given model. So as to see, okay, fine, with the given data, the model performs well. But how does the model perform seeing alien data, which the model hasn't ever seen, the unseen data, right? So this is the two steps that we'll be doing. First, splitting the data into X and Y. Once that is done, we'll split the data into two parts, training and testing. Train the model using the training data and test it using the testing data. And with that, we also find the performance of the model using the evaluation metrics, which we'll be learning in the next lecture, right? All right. So let's quickly split the data into two parts, X and Y. So I'll say um, X equals to df of area, right? And Y equals to df of price. So we are done with the splitting. So splitting the data into X and Y, or target and features. Followed by what we do is we do the trend test split. So dividing the data into training and testing set. We call it as trend test split. So trend test split from sklearn.model. I think from sklearn.model selection. From sklearn.model selection, import trend test split. Great. Now what we'll do is xtrain xtest ytrain ytest equals to train test split of xy. So always take the x components first, followed by the y components. Or you can do vice versa. Then we say trend test split y comma x. But this is the usual we follow in the industry norms. So first train, then test. And between x and y, first x, then y. So x train comma x test comma y train comma y test equals to trend test split x comma y. All right. Then we have to give the size by which we want the split to happen. So here, let's say 30% of the data goes for testing and the remaining 70% should go for training. So I'll say test size equals to 0.3. So 30%. And I also have to pass a random state. Random state, why is it necessary? So you might know that whenever we use the a random number, each time we run the cell, a new random number comes into the picture, right? And we do not necessarily want that here, at least, because when we are doing the trend test split, it will randomly split the 30% of the data from the entire data point. So each time we run this cell, a different data point would be taken out as a testing set, which would create problems going forth. So what we want to do is we want to, fix which portion of the data would you want to extract as 30%. So when you say random state, when you give a particular random state, it focuses only on one chunk of data that it would remove. Otherwise, it would have been removing different chunks of data. 30%, but different chunks of data. Visually making you understand. Even if you say I want 30% of the data, the 30% can lie somewhere over here, right? Or it can lie somewhere over here, right? Or it can lie somewhere over here, 30%. And this occurs in random. So what we do is we say random state equals to, we give any random number. Doesn't really matter. But when you fix the random state, so each time you run the cell, let's say this is the one it is targeting, then all the time this particular data would be scraped off. Okay, great. So I'll say random state equals to, let's say 2. That's done. So we are done with the training data and the testing data. Now let's start with the modeling, right? Okay. So what we'll do first is we'll call the linear regression model. So from um, sklearn.linear model, import linear regression. All right. And I'll just call an object to the class linear regression. Right. Great. Now I can use this model throughout. So what I'll say is model dot fit. So I want to fit with respect to X train and Y train. So I want to train the model on the training data set, that is X train and Y train. So I tell the model, okay, see, this is how Y changes with respect to change in X. All right. So I'll say X train, comma, Y train. By this line, I'm simply telling the model that, okay, just observe the change in change in Y with respect to change in X. So this is nothing but training. Next, I say prediction. So prediction, it would be a plural, predictions, or this is a variable, you can do whatever you want. So model dot predict X test. So now what I'm doing is I'm saying, okay, fine. So now you have got trained with respect to the training data. You have understood how Y changes with change in X. Now I'll give you some alien data, X test. That is that given data which we had extracted before. Now, can you find what would be the corresponding Y values? Earlier you already know, right? With change in X, how Y changed. So now I give you a new set of X values. Please predict and tell me how the Y looks like for this given set of X values. So this is my prediction. All right. Great. So let's just simply run this. Okay. What is the issue? Okay, fine. So basically it needs a reshape because the issue lies over here. X would always take a, yeah. Now it should work fine. Let's just see it again. Yeah, it should work fine. Okay, always remember, put double brackets for X and Y should have single brackets. All right. Um, Great. So now let's quickly visualize the same. So what I'll say is plt.scatter X test, comma, Y test. All right. And let's take the color as, let it be. Okay. So what we are trying to do over here is we are just trying to understand how the testing data points look like with respect to X, how the Y actually varies for the testing data, the unseen data. And this is our answer. This is how it varies. All right, great. Now what I want to do is I want to plot our best fit line and see how it, appears in the canvas. So what I'll say is plt.plot. And what do I want to plot? The X values, so X test with respect to the y values. Here, the y values are the predictions that it has made, right? So the predictions is simply over here. Okay. We can also change the color. Just let me give it as red or something. And let me put it as blue, right? And also let me just put this semicolon so that I don't get this line over here, right? This line you see. Cool. So this is how it looks like. This is my best fit line based on the x values and the predicted values made by the linear regression model, while these were the actual points. Now, obviously, we are not getting a very good line because the points are not fully linear. There are multiple values of y for the same values of x. We can see that. So obviously it would not give us a very good result, but yes, this is definitely the best fit line. With respect to this line, we can say for whatever values of x, we can actually determine the corresponding value of y. All right. So let's say going forth, you just want to predict any random value of x. So what was my x? Let's just take x test, right? We just did x test. Prediction is equal to model.predict x test, right? So what I want is predict a random area. X is area. Fine. So what I'll say is model.predict x test. So let us just say some random value like let's say 3000. So it gives me the value as 3730187. So it says this would be the price for a house having this much area. Okay. Now what did we understand? Here to create the linear regression model, we need to optimize the M and C, correct? M is the slope of the line. Now, if we look at it, right, this is the given line. The slope can be anything, right? The line could have been something like this. The line could have been something like this, whatever it is. But linear regression, the machine learning or Python chose it to be as this particular slope, right? That is having the angle as given theta. Can we find what is the value of this theta? The answer is yes, we definitely can. So let's just try to find it as well. So what I'll write is slope. How do we find it? Model dot coefficient, coef. So this is the value of m. Okay. And can we also find the c? C is the intercept, right? The intercept could also have changed, right? Instead of getting this intercept, it could have started something from here, or it could have started something from here. But scikit-learn chose it to give a intercept as is shown over here. Can I know the value of the intercept? The answer is again yes. So I'll say model.intercept. All right. And it gives me a value of this. So ideally, we can also build our own regression model by saying, okay, the price would be, so final equation, if I say, let's say price, what is the equation? We all know y equals to mx plus c. What is y? Y here is the price, right? What is m? M is model dot coef, right? The slope. So model dot coef. X is what? X is the value that I want to predict, 3000 over here. And what is c? C is the model dot intercept, right? So let's quickly find price equals to model dot coef, right? Model dot coef multiplied by m into x. The value of x I want to take over here is 3000. plus C. C is model.intercept, right? Okay. So let's just see what is the value of price. Sorry. So now if you see, the value of price is exactly the same. 3730187, 3730187. So this is exactly how a linear regression line is created. All right. And I hope you understood it pretty well. From the geometric intuition to how we actually build a linear regression model using coding, right? In the next lecture, we'll be learning about how to evaluate the performance of this machine learning of this linear regression model. So we'll basically learn about the evaluation metrics. See you in the next lecture. Thank you.